Indeed, Danuta. Thank you for the introduction, and thank you also to Rebecca and Pedro for inviting me to this webinar series. Greetings to all of you. I hope you're all well, and thank you for zooming in. This is a presentation about the 3-tau model. Now, the 3-tau model is a model that's capable of providing quality fits to fast field cycling NMR dispersion curves over the full frequency range of the curve for a wide variety of fluid-filled porous systems. So we shall see that the model is capable not only of producing 3-tau time constants, but also a range of additional derived parameters, which I hope might be useful to you. So what exactly is the 3-tau model? Well, this is a simplification of a pore in a solid material, a fluid-filled pore in a solid material. So the solid here is indicated in the black, and on top of the solid is a surface layer of liquid, which we'll presume for the time being at least it's water, a single layer of water. And then the remainder of the pore is filled with the bulk water. In the first manifestation of this model, we will presume that there are paramagnetic ions located in the solid material of the pore. And under these circumstances, we can identify the key physics that leads to the NMR dispersion curves that many of you guys measure in these systems. So the key physics is as follows. First of all, the relaxation rates that are generated are associated with the motion of the nuclear spin. So these are the proton spins of the water relative to the fixed electronic paramagnetic spins which are in the solid. There's two example interaction types here. So what we're looking at is a water molecule in the layer, a water molecule in the bulk, and these red lines indicate the interaction of some paramagnetic ion in the solid with a proton in a water molecule in the surface layer, or alternatively, a proton in the bulk water. Of these two, it's the dipolar interaction with the water in the surface layer that dominates, and there's two reasons for this. First of all, clearly, the surface layer of water is closest to the paramagnetic ions, and the dipolar interaction is very strongly dependent on distance. The second reason is that the surface layer of the water moves at a slower rate across the surface, and that also serves to increase the relaxation rate response. The third piece of key physics that's been identified as being useful for these systems, which is incorporated in the 3-tau model, is that the density of the paramagnetic ions in the solid is assumed to be representative or representable by an effective layer of ions, which is illustrated by the white dashed lines in the figure here. Now, many of you out there will think, well, this seems very familiar. This looks like a Korb model, and exactly that's the basis of the 3-tau model is a Korb model. And Jean-Pierre Korb, many years ago, identified exactly these key physics for these types of systems. If you like, this manifestation of the 3-tau model can simply be considered as an enhanced Korb model, and we stand on the shoulders of a giant in that respect. But what are the enhancements that the 3-tau model brings to a Korb model? And there's three of these. The first thing that we do, which is different, is that we also include the relative motion of the bulk protons on the water, the bulk water, relative to the fixed paramagnetic ions, not just the surface layer water as Korb does in his models. So that is added in. The second thing we do is to place the effective layer of paramagnetic ion density, which is in the solid, actually within the solid itself. In the Korb models, that layer, quite reasonably, is placed in this blue surface layer right here, aligned with the surface layer water, arguing that it's the surface paramagnetic ions that's critical to the relaxation, and it's those at the surface which are most important. The third thing we do is that all the calculations that we do are undertaken either analytically, where that's possible, but if not, we do it numerically. So there's no approximations in the process of working out the relaxations rates based on a model such as this. So what are the calculations we have to do? So here's my apology, but there's going to be one quite unpleasant equation here, but we'll move through this briefly, but it does illustrate some of the restrictions of the 3-tower model. Okay, again, as many as you will know, there's 3 steps to calculating the relaxation rates for dynamical systems. The first of these involves determining what's called a time-dependent dipolar correlation function, usually given the symbol G of T. And this is the equation you need to solve. Bang. Okay, this is horrible. Yes, it really is horrible. But it's composed of 3 components, and this is useful to identify these. These R vectors that we can see here are not position vectors, they are spin pair vectors. And the illustrative example here is actually spin pair vectors between water molecules. So R0 is the vector that connects a pair of spins at time 0, and R the same pair of spins at a later time R. So the first job we have to do when working out a model is to determine this probability density function. This gives us the probability that a pair of spins separated by R0 at time 0 are at a later time t separated by a vector R. So that's the dynamics. The interactions are captured by the middle term here. So these are dipolar interactions. The y's are spherical harmonic functions, but you can see that they're dipolar interactions because they have the characteristic r cubed or 1 over r cubed form that you can see here on the denominator. The final part of this expression is the geometry of the pore, which we've just defined in this particular case. And that's captured by the integral limits of our integrations here. Well, if you can do that, everything else is plain sailing. The next step is a simple, numerical Fourier transform of that function to generate a spectral density function, which is trivially converted to a relaxation rate. T1 to the -1 in this case, but it could be T2 to the -1, it doesn't matter. In passing, I will mention that this model is valid in the fast diffusion limit. Now, this means that all the water in the pore must sample both the environments of the water, that is the bulk here and the surface layer here, during the time scale of the measurement. And the time scale of measurement is deemed to be the value of T1. T1 at its minimum is around about a millisecond, and we will see that the correlation times for the motion of the bulk water or the surface layer water can be as long as about a microsecond. So throughout, this fast diffusion limit is satisfied. This quantity X is one of our fit parameters. It comprises the fraction of the water that is at the layer of the pores, the fraction of the water in the layer of the pores. Okay, that looks really scary, but don't worry, you don't have to do any of these calculations. We have done them for you. And when I say we, I'm also talking about my 2 dear colleagues at the University of Bologna, William Bortolotti and Rémi Cogan, who have been extremely helpful over the last few years in helping develop some of the software that we use to execute these fits. These are available to you. So if you think at the end of this presentation, these pieces of software can be useful to you, just contact us or one of us at these email addresses here, and we'll happily send you the software through. Note of caution, it's a bit expert friendly, but what it does, it reads in the pre-calculated data sets for you. You have to provide your experimental data. It goes into a MATLAB script, and out comes the fit parameters. The Bologna version has a nice interface here, and but there's two versions of the software which do broadly similar things. So I hope that eases your concerns in that respect. Okay, we've looked at the system with paramagnetics. There is a second version of the 3-tau model which does not have paramagnetics in it. So these are for systems that are devoid of any paramagnetic impurities. And we have a 3-tau model for that. And that is unique. There's no parallel to that, as far as I'm aware, anywhere. And the interactions that are of interest here are shown schematically. We need the layer-layer proton-proton interactions, the bulk-bulk proton interactions, and the layer-bulk proton interactions to be considered in this instance. Okay, so what exactly are these 3 time constants? These are constants that emerge from the fits to your dispersion data. And we'll see plenty of examples of dispersion data later on. The 3 constants are labeled tau L, tau D, and tau B, hence 3 tau. If we look at the bulk water in the first instance, then the bulk water moves or diffuse. Here's an example with the red squiggly lines. And, oh, beg your pardon. This gives us the bulk diffusion time constant tau B for bulk. So this is just defined in terms of the diffusion coefficient of the water with respect to one of our standard, a standard unit length, which is delta, which is 0.27 nanometers. Delta of 0.27 nanometers is chosen as roughly the distance between 2 water molecules in the bulk fluid. So tau B, which is about 5 picoseconds for bulk water at room temperature, is the time it takes for a water molecule to diffuse 0.27 nanometers. We have a similar definition for the water in the surface layer. It is tau L, L for layer, and the surface layer diffusion time constant is defined in an identical way. Tau D is the desorption time constant is somewhat different. This is a time constant that describes how long a water molecule stays in the surface layer, effectively. So if your picture is a whole set of spins at time 0 in the surface layer over a period of time, some of those will desorb into the bulk and vanish. And the characteristic time constants for the decay of that number of spins is given by the e to the minus t over tau d, d for distortion, desorption, tau d is the desorption time constant. So they are the 3 time constants. Just before we move on to look at some fits, what we must do is hardwire a couple of parameters. These parameters are set based on molecular dynamic simulations in part, and part by comparison with a set of data, fast field cycling data from Barbaron and co-workers published in 2003 that we'll spend a lot of time with over the next few slides validating the model. So the first of these parameters is the thickness of our surface layer, which is defined to be delta, 0.27 nanometers. And that comes from electrodynamic simulations by us and by numerous other people. There's a slow-moving layer of water at a surface of about that thickness. The second hardwired parameter in the model is the distance of this effective layer of paramagnetic impurities below the surface that is representative of the density of paramagnetic ions in the solid, which is fixed at 2 delta. And we'll see shortly how that comes about. Okay, so now we're in a position to, if you like, validate the 3 tau model. So we can fit to data But the fits are only worthwhile if the numbers that come out for the various time constants and other parameters, if they are actually meaningful in some way. What you see on the left is the data produced by Barbaron and co-workers in 2003, which is extremely impressive work in a number of ways, not least because they've published in Physical Review Letters a paper on mortar, which is a very impressive achievement, I have to say. But the reason we chose this particular set of data, and it is a set of data, is because it relates to a hydrated mortar. And we were funded at the time by a European project on cementitious material. And so obviously mortar, which is based on cement powder, it was of interest to us. Moreover, these authors produced a series of fast field cycling curves as the mortar was setting after it was hydrated. And what you see in front of you is the final set of data after 12 hours. The downside of using this data is it's somewhat scatty, but an upside is that in addition, these authors also undertook electron spin resonance measurements and determined the density of the paramagnetic ions in the solid and identified that as being iron 3+ ions. Okay, so we can now look at this data in more detail, and we're in trouble straight away. If we look at the value of tau L that comes from the 3 tau model, it's sub microsecond, but this compares poorly with a Korb model of 1.3 nanoseconds. Now, we were confident that we had good numbers here for tau L and tau D because we had undertaken a whole series of molecular dynamic simulations of different surfaces, and we always found that these two physical quantities were broadly similar. And that's what we see by way of outcome of our fit, this blue curve, to this data. But we need to understand why we have a big difference and our result. And in doing this, we discovered something quite interesting. So what you're looking at now is an explanation for the tau L discrepancy. It's just a difference in the style of the models. The two curves that you see, the green dotted curve and the straight black line, are results for a 2D system, which is essentially the Korb model, with two water molecules here in the surface layer water, which is presumed to be a pure 2D system with the water diffusing with respect to fixed paramagnetic ions at the surface, i.e. within this 2D layer. The green curve here is determined from a Korb model which is empathetic to the long-range diffusion of two-dimensional systems, which is known to go as T to the -1. The solid black curve is the known result for 2D diffusion at the low frequency limit. And you see there's a beautiful match in the low frequency range between the known low frequency limit in this instance and the Korb constructed correlation function that we need as the first step of the calculation, which is then Fourier transformed, etc., to get the relaxation rate. So all is going well at this point. However, this is a construction. This expression in the green box is a construction. It is not a solution to the diffusion equation for the movement of water molecules in a 2D plane relative to a fixed paramagnetic ion. If you do that calculation, which we did, this is what you get. Now, the Korb model is successful because the slope of this curve is very characteristic of a whole range of fast field cycling NMR dispersion curves that you see. This is why it fits so well and why it works so well. But this is an accurate result for 2D diffusion. And I can hear you say, well, Foxy, you must have done this wrong, for goodness sake. You've just told us that we have T to the -1 long time behavior of 2D systems. and it's a beautiful match with the low frequency result. Yes, that's all true. But surely your result, which is also for the same system, does not match the solid black line here, and therefore it must be wrong. Well, it does match that solid black line, but only right down in this very, very low frequency limit. And we have checked that. So what is this is saying, and this is a really important point, what this is saying is that the long time behavior of a diffusing system, whether it's in 1D, 2D, or 3D, is not represented by the gradient of the curve that you see in your dispersion measurements. Okay? You cannot, from one of your fast field cycling NMR dispersion curves, from the slope of the inflection component, deduce the nature of the diffusion process from that, because it takes so long to reach this long time limit. It is way off the low end frequency of the frequency range of your experiments. And that's a really very important point. It's further illustrated when we put in the 3 tau model equivalent to this. So this is the 3 tau model curve, where you can see that the slope here is very similar to the slope here, and it's also indicative of it's a similar slope. So it's indicative of what you get in your dispersion curves. But the long time limit of these systems, our 3 tau model system, is t to the minus 2. T to the minus 2 is different from t to the minus 1, yet you get the same slope. Not only that, but the 3 tau model produces this nice rollover of the curve here, which is a feature that's seen in many dispersion curves. Okay, the difference, as you can see here, between the two curves, between the Corb and the 3 tau model, is about 100, and that explains the difference between the two values here, 1.3 nanoseconds and our value. So we now understand how that has arisen, and we give ourselves a green tick here. We're now going to move on to look at the other time constants in a little bit more detail, tau d, tau l, and in particular the ratio tau d over tau l, which is supposedly indicative of a strength of interaction between the surface and the surface layer fluid. Indeed, these ratios represent the number of hops of a water molecule at the surface before desorption. We explored these numbers using molecular dynamics simulations. And I have to say, we've used MD a lot. Molecular dynamics is fantastic at establishing and understanding the essential physics. It has to be used with caution in determining quantitative values of time constants, for example. And there's no way with MD we can access the microsecond timescales we need for tau L and tau D. So we took a system, water, solid, this is a porous system with boundary conditions, a layer, a planar layer of fluid, and we took it to its simplest element. So a water molecule is one of these silver spheres, the solid is here in the middle, and all the interactions are really simple Lennard-Jones interactions. The water-water interactions, we choose A and B, that yield the correct diffusion coefficient for the water. We then are able to apply a Lennard-Jones interaction between the solid atoms and the water atoms at the surface, and just scale that accordingly to our desires. So we multiply by a factor, change the A and the B, so we can tune the interaction strength of the solid-water interaction. Well, what do we get? Well, we start with a look at tau L, because we wanted to persuade ourselves that the diffusion of the water at the surface was an Arrhenius energy-activated diffusion process. And sure enough, it is. So up the vertical axis here, we have the natural logarithm of tau L, the layer diffusion time constant. And on the horizontal axis, we have something called an interaction parameter. This is a multiplier of the water-water interaction, if you like. So the 1 here means that the solid water interaction is identical to that of the water-water interaction. Here's the MD data. We can only go so far. And we can see, we can put a straight line through this, which confirms that this is an energy activated Arrhenius style diffusion process. If we put a marker in here, that's 1 nanosecond for tau L, but that's not what we see. What we've just seen with our mortar system is a tau L of about 0.27 microseconds. And later, or shortly, we'll see a plaster paste sample with a larger tau L of 2.4 microseconds. So it is tempting here, and with great excitement, to say, well, hold on a minute. With our mortar system, we can get a quantitative value of the energy interaction of the solid with the surface liquid in our mortar system. And it is 2.5 times the interaction energy associated with water-water interactions. That would be really nice if that was the case. In fact, one has to be really rather cautious here, because it transpires that this slope of this blue curve or blue line that you see in front of you is dependent on the density of the water sites at the surface. And that makes sense, because if you've got water sites that are further apart, then if a water molecule is seeking to move to a neighboring site, it finds it more difficult to do so. Even though the interaction strength with it and the solid is similar. Okay, so that was interesting. But now we move to tau D over tau L. And this is believed to be a measure of the strength of the interaction with the surface. And indeed, these results indicate that that is indeed the case. Moreover, what we see from the molecular dynamics is beautiful. Their numbers lie in the range 1 to 8, 1 up to 8 here, which is exactly what we see as a range of the ratio tau D, tau L, as you will see shortly, in a range of systems for which the statistical scatter of the data is really quite low. If we have a lot of statistical scatter, as with the mortar system, then, well, sometimes you get larger values of this ratio up to perhaps about 15. The other thing we discovered by doing these MD simulations is how long the water stays at the surface. It was longer than we anticipated. Bear in mind that the bulk water here has a time constant for motion of 5 picoseconds. And we found out the reason for this, and we sort of dubbed it the nightclub effect. So I don't know if any of you go down a nightclub. I certainly don't. But imagine yourself as a blob here hanging onto the wall with your drink. You can move as fast as these fast-moving molecules out here. But where can you go? You can't go into the wall. You can't move left. There's somebody else there. You can't move to the right. There's somebody else there. So you make a bid for freedom. You move out towards a dance floor where all these fast-moving objects are, but you're battered and sent back to where you came from. So the consequence of this is it's difficult to get away from the surface. Indeed, if there is absolutely no interaction between the surface and the water at the surface, tau D is still 10 times longer than the characteristic time constant for the diffusion of the bulk water here, 50 picoseconds. Moreover, it's a factor of 100 longer if the surface to water interaction parameter is 1. So if the solid is interacting with the water with the same interaction as water-water, tau D is some 100 times longer than the corresponding time constant for the movement of the bulk water. Okay, we got a selection of green ticks now. We're happy with these set of time constants. Are we also happy with the bulk diffusion time constant tau B? Yes, we are. We get a value of 21 picoseconds here. Well, we find generally that this constant comes out from the fit somewhere between 10 and 25 picoseconds, typically. Why is it longer than 5 picoseconds? Well, we understand this as well. So just a reminder of our system here. We're seeing from the fits that the motion of the surface layer is slow, time constant of order microseconds. We know that the time constant associated with the pure water at room temperature in the bulk is 5 picoseconds. But there is another layer of water here, a second hydration layer, which has a characteristic diffusion time constant similar to the bulk, but not quite the same. And in a variety of molecular dynamic simulations by us and by many others actually, we typically see slower diffusion by about a factor of 2 to 3. So the time constant would be 10 to 15 picoseconds. Well, we saw 21 in our data, but of course, your actual liquid is going to have ions and all sorts of clutter in the water, which will slow that down even further. Okay, so we get a green tick there as well. So we're doing great. We can give ourselves immediately another green tick, but NM is the paramagnetic ion spin density in the solid. And remember I said that these authors, Barbaron and co, measured this using electron spin resonance, and our system is set up to match those two values. So the position of the effective layer was designed to reproduce this result, and indeed it does very well. Right, now we move on to two other parameters. X, you may recall, is the fraction of the water at the surface of the pore. Well, what we can do is to convert that to a distance. And I've called this the volume weighted, so the water volume weighted planar pore equivalent thickness. And this is designed to give some kind of value associated with, well, I suppose the granularity of the system, the typical thickness of the pores, if you like. And we do this in a very simple way, as illustrated here. So here's our pore. We have solid at the top and the bottom because we're interested in both surfaces of the pore now. So we have a planar pore. We know that the surface layer of water is our standard distance, 0.27 nanometers. If we look at the total thickness of the planar pore, we call that H. We have from our fit result the surface water fraction, the surface to volume ratio, also called. And so it's a simple matter to relate these quantities. So we know X from the fit, delta is 0.27. It's a simple matter of generating an H, which I say is a sort of characteristic distance parameter for the thickness of a pore if all the pores in your material were planar pores of this thickness. We see actually that turns out to be quite useful. Is the value we get here, 0.74 microns, reasonable for a mortar? I don't honestly know, but I know it's not millimeters and I know it's not nanometers. I guess that's pretty reasonable. So I'll put question marks there because we don't actually know whether they're right or wrong, but it's certainly not unreasonable. Finally, the T1 to T2 ratio, which we can determine from our fit at 20 megahertz. So all the T1 to T2 ratios are determined at 20 megahertz. And I confess to a faux pas here in the original attempt to fit our model to this hydrated mortar data, because we sought to add an additional fit criterion that T1 to T2 should equal, well, something in the range 3.8 to 4. And a decision to do that was based on some experimental work by my colleague, Peter MacDonald at Surrey in 2005 on white cement paste that yielded this ratio T1 to T2. The actual fit value that we get from our hydrated mortar, fit to the hydrated mortar from the 3-tau model, is 3.1. And you can see that that was a mistake. There's a significant difference between these two values. Now, hold that thought just for a moment, but we're going to do 2 more steps before I think we might be able to resolve that difference. The argument I would say for doing that is that white cement paste, the binding element is calcium silicate hydrate, and that's the solid that matches or is on the surface of the pore where the water is. Hydrated mortar, well, mortar is just cement powder added to a little bit of lime and added to a fine sand. So it is the same binder in each case. They both have calcium silicate hydrate. So it seemed perfectly reasonable to try and match the experimental result for white cement paste to that of mortar. Just before we move on, I just want to acknowledge some excellent work by Remy and William once again. They were anxious to understand, quite rightly, how good or bad the 3-tau model was in dealing with scatty data. So we took a 3-tau M curve with known parameters, added some white noise, some scatter to the data, and then refitted it using the 3-tau model. So we're seeing how well the 3-tau model reproduces the original values. So on the right here, we have the synthetic experimental data. This is what we're seeking to reproduce. And you see in pretty much every case, there's a really good match between the values here, perfectly reasonable. The least good is tau d, and there is a health warning here. Tau d is your desorption time constant, is the longest time constant. If it's the longest time constant, it impacts the lowest frequency range of your dispersion curve. And therefore, that's where the biggest scatter tends to be in experimental data, around this region here. And so this is demonstrating what we tend to see when we do fits. Tau d is the least reliable in general of the time constants that we generate from the 3-tau model. Okay, right, now we can move on and look at systems without paramagnetic impurities. There's no other model that can cope with these systems. And just look at this, ladies and gentlemen, there's an awesome fit to the data using the 3-tau model. This is a plaster paste data from, again, Jean-Pierre Courbe, published in 2011. And all the numbers here are absolutely lovely. I draw 2 particular points to your attention. First of all, such is the quality of the experimental data, we can actually measure, we believe, the surface water spin density to get the optimum fit. And here it is 73 spins per nanometer cubed. Compare that to bulk water spin density of about 67 spins per nanometer cubed, so a little bit more dense. So that just shows how good the data is, and indeed how good the fit is. So this is just water-water interactions that fit this data here. The second thing I want to point out, now just look at this. The T1 to T2 ratio comes out at 3.9. Well, that's exactly in the range that 2 slides ago I was talking about for white cement paste. Well, how can that be? Is that just coincidence? Plaster paste is calcium sulfate hydrate, I believe, and cement powder has some calcium sulfate in it. But the binding elements are largely different. The solid is different. And yet, if I gave you samples of both of these, they're both white materials. If you add water to them, they go hard. And if I gave you a sample, you'd struggle to determine one from the other. So what does that mean? Is T1 over T2 something that measures the fineness, granularity, if you like, of the material? Because mortar is more granular than plaster for sure, and for white cement paste as well, presumably. Actually, that's seen here with H, which is much, much less. Hold that thought for a while. Another system we looked at without paramagnetics was a saponite clay. This is a sort of laminar clay, synthetic clay structure that was created, I say synthetically, so without paramagnetic impurities in. Again, a sublime fit through the data. Once again, we can see we're able to fit and determine the spin density at the surface, 76 in this case. And there's two other important points to point out. First of all, and much to our delight, we found some data here in which the authors, using a completely different model to the Korb model, produced a value for tau L that was very similar to ours. And that's very reassuring that we have a good model here. But look at this, 9.6 for the ratio T1 to T2. Well, clay is a rock-like material. If you read any of the literature on hydrocarbon rocks, they're always saying that this ratio is indeed in the range 5 to 10 for a rock. T1 over T2 seems to come up trumps again. I don't understand why, but it's again seems to be really rather reassuring. Maybe it's good fortune. There's no T1 to T2 at 20 megahertz for this particular saponite clay to compare directly with. Okay, so let's move on. Here we're looking at a silica sample that was analysed. Now, everything was thrown at this sample, hook, line and sinker. And we had to do this because if you look at the vertical scale of the dispersion curves here, these are now small numbers. So the relaxation is dominated still by the interaction of the rather dilute concentration of paramagnetic ions in the solid, presumed to be iron, but without the knowledge of that, for sure. But these are such small numbers that the water contributions also play a part. And that's what the blue curve is here. So these two components are added together. Now, the important point here is that the addition of the water-water component adds 0 additional fit parameters to the model. And that's because it's based on exactly the same 3 taus, as well as the same surface to volume ratio, the same value of X. And of course, the spin density of water is well known, assumed to be about 67 spins per nanometer cubed. We also have to add an additional element here, which is a roughly constant offset, which we believe is associated with a small concentration of iron impurities going into the water in the pore from the solid material. What we have here and what you're seeing here is actually a dispersion curve obtained from a completely separate project involving Dermot Brougham in Dublin and his team, and also one of our students, Ursh Eistock, has been involved in this as well, on aqueous paramagnetic ions, and we've just used that data here. That's really not important. It's just a flat offset that we've added in here to get this, again, supremely high quality fit. Just before we move on to look at another silica sample, just hold in your thoughts the 1.4 microns for H as a sort of characteristic distance parameter, size parameter of the pores, and the 3.1 normal number for the T1 to T2 ratio. Because in the next step, we're moving to Q10 silica sample imbibed with water. The 10 of the Q10, as I understand it, stands for nanometers. And this is a different silica sample in which, according to the provider of this data, who I thank profusely, Jordan Ward-Williams at the University of Cambridge, who tells me that the picture would be sort of voids and channels in a sort of 3-dimensional system, which to a really good approximation apparently is of 10 nanometers thickness. we're seeing a whole set of good numbers again, and again we're throwing everything at this model here. So we have a weak concentration of paramagnetic ions, the water-water contribution, and a very, very small, virtually negligible ion spin density right down here. Two things to point out. H, the characteristic thickness of the pores that comes out of the fit, is much smaller than the previous silica sample we've just seen by a factor of about 4 or so. But it's 430 nanometers, notice. It's not 10 nanometers. I would say that this is a volume-weighted planar pore equivalent thickness. So if there was cracks or other volumes of space full of water, that would up this value of H. And whether that's the case or not, I really don't know. The other thing to identify, and this gave me the heebie-jeebies when I first saw this, 18 for T1 over T2, but Jordan tells me that that's typical for this sort of material. The high value of T1 to T2, he says 15 to 20 is typical for this material. And again, we nail it right there for T1 over T2 in this instance. So all that's looking very good. The question that we're asking, because this system is at 10 nanometers, I've always considered that to be the limit of the standard 3 tau model. Any systems less than that, truly nanoscale systems, probably not suited to the 3 tau model in its current inception. Can we have a 3 tau model for genuinely nanoscale systems? And the answer is yes, we can. And we later published some work in 2018 on just that. And we looked at 3 types of nanoscale porous systems where the confinement is in sort of 0-dimensional, like quantum dot systems, in which the nanoscale dimension is in all 3 directions. 1D systems in which the nanoscale sizes are in 2 directions, and our planar pores, which are 2-dimensional with the nanoscale restriction in just 1 direction. Look at this. This is one excerpt from the paper down below, 2018. And what you're seeing here, again, dispersion curves predicted, because there was no experimental data to compare with, for planar, channel, and closed pores at 2 and 4 nanometers. Shortly after this was published, I was asked to review a paper by Link and co-workers on, again, silica. And if you look at the Q values here, Q3, 6, 15, and 30, again, this is the nanometerage of the silica material. So 3 nanometers, 6 nanometers, 15 and 30 here. Let me point out a sequence of our 3 tau model curves here. And what you've got to focus on are the red dashed lines here, because we're really only interested in the channel pores. So you're looking at the 2 red curves here. Now, we have the relaxation rate plotted as a function of frequency. The authors, Link and co-workers, have the relaxation time as a function of frequency, so they've flipped over. But if you look at their sequence here, and you look at the red curves here, and imagine it flipped over, then the similarity between those 2 sets of data is really quite encouraging, I'd say politely. Now, yes, they're using 3 and 6 nanometers. We're using 2 and 4 nanometers. They've used heptane. We have water. But nonetheless, qualitatively, this is very, very reassuring indeed that we have something here. Okay. And now another set of data provided by Jordan, bless him. He hasn't seen this, I'm afraid. Again, I've thrown everything at this one. We have both the interaction of the paramagnetic ions with, in this case, not water, but methanol in Q10 silica, so the same Q10 material, and fits using that and methanol contribution and an offset as well. And what Jordan has been able to do quite brilliantly, and as you heard a few weeks ago in his seminar, he's able to produce two dispersion curves, one associated with the protons in the OH group of the methanol, and the second associated with the H protons in the CH3 part of the methanol molecule. So that's why we have two dispersion curves here. And the solid lines, again, the black lines are the 3 tau model fits. This is a bit of a rag bag, to be honest. There's a good, bad, and the ugly here. And if Jordan's gone to sleep or gone out for a walk or something, then maybe that's a good thing. Let's start with the good news. The tau B is really good. The diffusion coefficient of methanol is such that tau B would be about 8 picoseconds. These values are fantastic. At first, these values for the density of the ions in the solid, you think must be wrong. These two numbers you might think should be absolutely identical, because it doesn't matter whether you're looking at the H in the OH or the H in the Cs. Surely the density of ions in the solid should be the same in both cases. But it's clear that they're not, because the magnitude of each of these two curves here, right? It's a factor of almost an order of magnitude between them. Well, the explanation for this, I think, is absolutely clear. This gives you the orientation of the molecule at the surface, and the OH group is pointing downwards, which is what you'd expect, I think, because the OH is the more ionic part of the molecule. So that explains that. I'm going to give myself 2 ticks for that particular set of results. Where the problems arise is with the time constants, and these are really most peculiar. Yes, they're very small. One would expect that. We expect weak interactions between the solid and the methanol compared to the solid and water. Startlingly, tau D over tau L is 0.1. Now I'm saying we should get values between 1 to 10 or something of that order, and we don't get that. I'm thinking that we have a situation in here where the 3 tau model is not the most suitable model for this system. It is my belief that tau L almost doesn't exist, that there's very, very little surface diffusion of these molecules on the surface. Now, I've seen some molecular dynamics simulation of small alkanes in the past, and these small molecules sort of sit at the surface. They wave around somewhat, but they're not hopping across the surface. And so my picture is this, where tau L is much longer than tau D. So I'm thinking that probably this tau D over tau L ratio is right, and it's just indicating that. So I'm putting some question marks here. There's sort of a bit of speculation. I'm also putting a question mark by the H, because if you look at the OH H, we have 4 nanometers here as the thickness of our system, of the pores in the system. Well, that's pretty close to the 10 nanometers given here, but absolutely miles away from the 1.5 microns here. So quite what is happening there, I have no clue. Also, another area where I have absolutely no clue is the T1 over T2 is, well, between 1 and 2, right? So this is for methanol. T1 over T2 is between 1 and 2. And for the water that we've just looked at, we had 18 for T1 over T2. Now, I understand from rock people that I believe, I might have got this wrong, but I believe that if you have an organic at the surface of a pore, then you get this ratio being 1 to 2. And if you have water at the surface of the pore, you get larger values of T1 over T2. Well, whether that's true or not, that's certainly what we're seeing with these Q10 silica systems. Okay, before we move on to our final system to look at, T1 over T2 keeps cropping up. once again, dear friends, Remy and William have come up trumps with some more work looking at the T1, T2 ratio. And what they've done is to explore how this ratio changes with each of these three parameters, keeping the remaining two parameters fixed. So, for example, the blue curve on the left is showing that the T1 to T2 ratio drops as tau L increases, tau D and H being fixed. Whereas by contrast, T1 over T2 is increasing as a function of tau D with the other parameters fixed. And on the right-hand side, we have T1 over T2 decreasing as H increases. Remember, this is the thickness of the pore, effective thickness of the pore, with the time constants fixed. Now, what this does, really interestingly, is resolves the difference in T1 over T2 for a mortar system, which was 3.1 from the fit, and the cement paste, which came in at about 3.8 to 4. Because the H for the mortar is larger, a good deal larger than for the cement paste. And at larger values, we have smaller values of T1 over T2. So the time constants here are constant. So the CSH water interface in both these cement paste and the mortar is the same. They have the same tau L and tau D. It is H, the physical size on average of the pores, that's leading to a reduced value of the ratio for the case of the mortar. Now, this is work in progress, which is my way of saying that I don't understand this. I have absolutely no clue what's going on here, and I'm going to move on. And I'm going to move on to look at our final system, and we're interested in whether the 3-tau model can be applied to soft material systems. So we looked at a soft material system, and it was mozzarella, a pizza topping. 3-tau model moves into pizza toppings. And it will be no surprise to you to discover that Remy and William, once again, the University of Bologna and their respective team, have been involved in this work. They've done all what you're seeing now, okay? And of course, they're Italians, they're in Italy, so that's bound to be the case. But perhaps I should explain why they're so involved in what we've been doing. We're all involved in this project called ERICA. And this ERICA project is the latest European Marie Curie project that 5 centres involved in, including Surrey and Bologna, to try to improve cement-based products. Cement products in the world contribute 8% of all CO2 emissions, behind land use and hydrocarbon burning. So there's a big thrust to try and reduce the carbon footprint of these materials. Cement-based materials are the second most consumed materials by humans. The first, of course, is water, but the third must be pizza, because it's given them the authority to undertake their fast food cycling there, fast food cycling measurements of mozzarella cheese. If you look at the nanostructure of mozzarella cheese, it looks exactly like this, apparently. Where we have casein as the protein part of the cheese being the solid, and the paramagnetic ion impurities, well, impurities, magnesium, there's a lot of magnesium in there. Their authority for doing this is a quotation from an article by a well-known name, which is presented there. But let's have a look at the data and see what we have. And here it is. And it's really rather good. Lots of very typical standard numbers in here. One query I would say and they identified this, the low value of tau B and a rather weak fit to the data at the right-hand end here. Everything else is really quite remarkably good. We can look at the magnesium density in the solid. So the 3-tau model data is astoundingly close to the value taken from the FDA website for mozzarella cheese. Also, the thickness of the pores comes at 6.1 from the fit, and experimental values are typically 1 to 10 microns. Remarkable. Okay, so that's where we conclude here. That's the end of the presentation. I hope that there's something there that has tickled your fancy, and thank you for your attention. I'm happy to attend to any questions that you might have.